Hey everybody, welcome to another edition of Open Space. This is, of course, my live weekly interaction with you where you've got some questions about space and/or astronomy, and I am here to interact, answer the questions you've got, chat about things that are happening in the news, and really just kind of be the bridge between all the news we're publishing on Universe Today and some of the other more esoteric concepts in space and astronomy. If you missed last week's virtual star party on Saturday, it was incredible. I think it was I don't know, I say this a lot, but I think it was like the best one that we've done. We had 4 astronomers, all of which were very well organized. And we just brought so many images just as quickly as possible. In 1 hour, we must have shown off, I don't know, 20, 30 objects. So it was terrific. It really kind of feels like a well-oiled machine when so many weeks the weather is terrible, we're not able to bring everything together, and then every now and then everybody's got clear weather, everybody's technology is behaving, and of course we had a full moon. But apart from that, although the images of the moon were terrific. So a big thanks, of course, to Nancy Graziano for helping to organize that behind the scenes. Heard all the cats. I couldn't do this without her. Wouldn't do this without her. It's so hard to organize. So she is working really hard to bring all of this together. So again, that was the virtual star party. What was it, 14? The one that we did on Saturday. Was just absolutely fantastic. A couple of interviews coming up. We're going to be having an interview with a researcher who is working on resource extraction and manufacturing on the moon. And I'll have more details once we've actually set up the schedule for that. But that's going to be coming up in probably next week. And of course, I need to schedule another time with Chris Carr. My power went out again today. This time I was readier. I've got a uninterruptible power supply. I've got a backup battery that's able to run my router off of, and I've got an adapter so that I can go from my car to my house power. So I can run an extension cable from my Leaf to be able to power my power various stuff in my house. So I'm super ready. Then once I got everything set up and good to go, then the power came back on. So it was only down for like an hour, but I was ready this time to get through a day without power. All right. So go ahead. If you've got any questions about space and/or astronomy, go ahead and hit me up and we'll get into the show. So far, there's none. Okay, great. Oh, all right. John Suffield asks, in these days of super powerful space and earthbound telescopes, is there still anything amateurs can do in the field of astronomy? Yes. Astronomy is one of the few fields that amateur astronomers make regular and very meaningful contributions to. It's really hard as an amateur to make any kind of contribution to particle physics or, medicine. But astronomy is one that you can. And so there are a bunch of projects. A good example of this is like the American Association of Variable Star Observers. So you've got people that are pointing their telescopes at very specific stars and watching how they brighten and dim over various periods of time. That's a way to calculate, say, Cepheid variables, to watch supernovae as they fade away, watch stars that may have novae. And there's a ton of scientists who use that data, and so you can make those kinds of observations. Amateur astronomers can discover asteroids, comets. They can now confirm exoplanets. So there's still a lot of meaningful contributions if you have a telescope. Even if you don't have a telescope, there's a lot of really great citizen science projects. There's of course what we do with CosmoQuest. The amateur community helped figure out where OSIRIS-REx was going to grab its sample from asteroid Bennu. But and then doing work to find more Kuiper Belt objects for New Horizons to go to, counting craters on the moon and Mars to figure out how old various pieces of terrain are. And there's Galaxy Zoo. There's a bunch of these citizen science projects. So there once was SETI at home. So I'm not sure if there are other projects that you can get involved in. But yeah, I would say that of all of the sciences, like maybe bird watching, ornithology is the other one that amateurs make a regular, meaningful contribution. In fact, I think we've got the worldwide bird count is happening in about 2 weeks. And so usually we'll go out and count birds in our local area and add our data to the system. So, but yeah, astronomy is one that you can definitely make a meaningful contribution. Just do a search and you'll find lots of places where you can. Aox Trader, if there was a quasar in our galaxy, how bright would it be? So I've actually got a video on the channel, which is something like, what if the supermassive black hole in the Milky Way turned into a quasar? And the answer is, you wouldn't even notice. It would not be one of the brighter objects in the sky. You would need a telescope to be able to spot the fact that there was a quasar at the heart of the Milky Way. Now, part of that is that it's not pointing at us. It would be pointing, if it's rotating, it would be pointing in whatever direction the supermassive black hole is pointing at. And that's not even still completely known yet, exactly the orientation of the black hole at the heart of the Milky Way. But yeah, no, you would have a really hard time being able to find it with a good telescope. Obviously, astronomers with very powerful astronomical observatories would be able to find it. But for most people, you wouldn't be able to find it. Cataclysm 1234. Do you think that space will end in a big rip? Well, the big rip is, of course, one of the sort of ways that the universe can end. And where this idea came from is astronomers were trying to measure the expansion rate of the universe. They assumed that, like, the Big Bang had set forth all of the motion of the expansion of the universe, but then the mutual gravity of all of the objects would be slowing down its expansion. And the question was, would the expansion just go on forever? Would it sort of slide to a stop at some point, or would it even get to a point where gravity, mutual gravity, would pull the universe backwards and bring it back together in this big crunch? And in 1998, astronomers found the fact that no, actually, not only is the universe not slowing down, it's actually accelerating as it's expanding. And this was this idea of dark energy. And the expectation was that the measurements was that even though the expansion of the universe was accelerating, the amount of new energy that was appearing was just, a set amount for every cubic meter of space. As more space appears, energy fills each one of those spaces and helps expand accelerate the expansion of the universe. But one disturbing idea was that, in fact, over time, the amount of this energy that's coming into the universe to accelerate its expansion is actually increasing for each cubic meter. And as you sort of think about that, then you might get to a part where right now the expansion of the universe is going to carry galaxy clusters apart, but maybe it'll carry galaxies apart, and maybe it'll tear galaxies themselves apart, and maybe it'll start to tear solar systems apart into the far, far future of the, and we're talking billions of years from now. And the answer right now is that we don't know. The best measurements of the expansion rate of the universe don't give an answer to whether or not dark energy is actually increasing or whether it's remained static over the history of the universe. And so we're going to need better telescopes to be able to get this answer. One is the Nancy Grace Roman telescope, which is going to be doing a lot of work trying to uncover the nature of dark energy. There's the dark energy, I forget what it's called, but there's a telescope that its only job is to try and scan for dark energy. So I would say within about 5 years, I think Nancy Grace's launching in 2025. So I'd say within about 5 years or so from now, we'll start to get an answer about whether or not the Big Rip is an actual future that is going to happen in the universe. And it's funny because, we talked about this a bit last week, how when you realize that when the universe has less time than you thought the universe had trillions, hundreds of trillions of years, but now it's only got 5 billion years before it tears itself to pieces. It sort of gets you right there. Just like, I thought I had more time. All right, let's move on. Trey Harmon. Solar sails. I thought they were pushed by the solar wind particles, but everything I see online now says that they're pushed by light. Photons, which have no mass. Is this right? Please explain. That is correct. Solar sails are powered by the momentum that is transferred by photons of light as they leave the sun, or a really super powerful laser. So they're not pushed by the particles that are coming from the solar wind. They're actually just photons. If you point a laser at a solar sail, you can make that solar sail move. And the photons themselves have no mass, but they do have momentum. And you can calculate that using E equals mc squared. So essentially, the most famous mathematical equation that we're all familiar with, E equals mc squared. What that tells you is essentially you can have on the one side the energy, the amount of laser light that you're firing. And on the other side, you've got the mass times the speed of light squared. And that mass part essentially helps you calculate the amount of momentum that is transferred. And so as the photons reflect off of the solar sail, they can impart this momentum into the solar sail to act as a propulsion system for it. When you fire a laser, you are actually imparting a tiny little bit of momentum on the laser in the opposite direction. And so if you had a laser just sitting out in the middle of space and it fired, the laser would kick back with a recoil because you're essentially throwing all of those photons out one end. All right. Gaurav Sharma asks, have we discovered rocky exoplanets that are not silicon dominant like most objects in our solar system? At the point, I guess what you're asking, when we look at the planets that are in the solar system, we break them up into a bunch of groups. You've got the rocky planets like Mercury, Earth, Mars. You've got the gas giants like Jupiter, Saturn. You've got the ice giants like Neptune, Uranus. Right now, the state of the art of observing extrasolar planets is you've got big ones and little ones. You've got dense ones and less dense ones. And that's pretty much it. And so when you see a dense, small planet orbiting around a star, then you say it's probably made of rock or silicon or metal or rock and metal or silicon or oxygen or whatever. But we are not at the point now where we're at knowing what they're made of with any kind of definition. We can tell just from the density. They're more dense than water. They're less dense than metal, but we don't really know anything about exactly what their composition is. You have to get a direct image of these planets and be able to observe the light that is coming off of their surfaces. And right now we can get a sense of what their atmospheres are like, but we can't tell what their surfaces are like. So we have no idea right now. Muchidakat. Which of your assumptions were challenged by reading Wallace Arthur's book and interviewing him? So for those of you who missed it, this is sort of like a shameless promotion for the interview that I did last week with Wallace Arthur with his book, Life in the Milky Way and Beyond. It was a terrific book, and I hope you have all had a chance to watch the interview, because I think it was a fantastic interview. We had a great time and kind of challenged each other. It was funny. After the interview, he reached out to me and he said, like, give me some more links to some of your thoughts about the Fermi paradox. And so it was actually a pretty productive interview. I hope we'll have a chance to have another conversation at some point. For me, what reading the book really taught me, and now the book has fallen on the ground, it's far away, but was it just showed me how life has solved the same problem again and again and again. And up until this point, I've always sort of fallen into this assumption that we only have this data set of one, that life has formed on the Earth, that's all we know of, and so we don't really have any idea of what life could be like in other places. But it really feels like life has solved the same problems with very, very similar solutions again and again and again. You know, trees, wings, skeletons, crabs. It's gone and developed the same kinds of body plans. And so that when you get liquid water, when you get terrain like mountains, hills, valleys, temperature variations, tidal flux from a large moon, things like that, you're going to have life forms that feel very familiar. So in fact, I really feel like we have a real head start in attempting to imagine and recognize life out there just because of the variety that we have here on Earth. We have actually many, many different examples of what life can do using the same basic raw elements, the same, oxygen, nitrogen, phosphorus, carbon, etc., as well as gravity, air pressure, temperature, access to energy sources, things like that. I found that really fascinating, and it totally changed the way that I think about just about life and what the universe is going to be containing, if it does contain life, what we should find as we look out there. So I found it really, it's great. I mean, I think that whenever you have an opinion about anything, I think it's really important to seek the best arguments that are different from yours so that you can really deeply understand what other people are, what the best formed arguments against and for what you believe are, and then just sort of let them rattle around in your head and battle each other, and you can form a far more nuanced position about what you believe and what you think. And so I kind of I chase this stuff. I want to find people who are certain that there's life everywhere, and I want them to tell me why they think it's everywhere. And then I can sort of incorporate that. So no, absolutely fascinating. Kyle Kramer asks, are you signing up for Starlink Beta now that it's available in Canada? I have already signed up for the Starlink Beta. So I know that some of my compatriots in Canada, in Nova Scotia, are starting to get access to it. And the moment I can get access to it, I will. I can't wait. Now, I solemnly swear that I will only use Starlink to transmit astronomical data to and from astronomical databases and to share pictures of astrophotos. That's really the only legitimate usage for Starlink. But no, I'm pretty excited to see how the service works. That's a great example of something that is very complicated. I think that a lot of people have a very just a knee-jerk reaction to Starlink or just satellite constellations in general. And yet when you think about the implications of people who have not been able to get access to high-speed internet, who suddenly do, allowing them to be able to connect to just educational resources and marketplaces and things like that. And when you consider the environmental damage that we're going to do in trying to create internet connections, it's a complicated subject, and you can't just come up with something that's really simple. So Anyway, that's my so Starlink. I am ambivalent about Starlink. I've mentioned this before. Like, if Starlink provides high speed, inexpensive internet access to underserved communities, then the loss of our night sky will be worth it. If it is just a way that rich discount traders can knock a couple of milliseconds off of their high frequency trading, then it will not have been worth it, and I will not be willing to pay that price. But that's my feeling. Sprinter 768, are you looking forward to the new movie adaptation of the Dune novel? No, I'm not. Let me explain why. I'm like half excited about it. I'm a huge fan of Dune. One of my favorite book series ever. Well, the first book. Second book was okay. They all went downhill from there. I didn't really bother after about the third book. But I love the original science fiction. I played the Dune video games and watched the original Dune movie, which was super weird. And like, what I don't like anymore at all is just superhero movies and sequels to giant sci-fi franchises. Like, I finally saw the new Star Wars movie. I don't even remember what it's called. The final lightsaber. I don't even remember. My wife and I are watching The Mandalorian right now. Like, I just don't care. But Baby Yoda is adorable, so I've got to stick around for Baby Yoda. And I obviously, 10-year-old me would just be freaking out, losing his mind, because he was such a nerd about science fiction and all this. But what I love is them adapting is the Netflixes and the Prime Video and HBO and stuff, realizing that there are all these incredible science fiction franchises that have been written, these incredible books that have been written that are self-contained, well-written stories, interesting characters, incredible concepts and themes, and they just need to be adapted. And a 8-part miniseries is exactly the right way to adapt a miniseries. We saw this with The Queen's Gambit. What a great TV show. 8 episodes. Story, beginning, ending. I loved every part of that. So I know that someone's going to be doing Foundation. Someone is going to be adapting other sci-fi concepts. And that's what I want more of. I would rather never see another Star Wars movie or superhero movie if that meant that we could see 20 really well adapted sci-fi stories, classics and new stuff. That would be amazing. So that's what I want more of. And so Dune, that's already been adapted. We've seen it, been there. Let's go for something that will just blow your mind, that you've never even heard of, that's going to be adapted. It's going to be super cool. Let's see the 3-body problem. Let's see We Are Legion, I Am Bob. Let's see, I don't know, all kinds of stuff. So that's my feeling. And just to tack on the end of this, Matt Jono 2, what are your thoughts on the Orville? I love the Orville. Orville is one of my favorite Star Trek shows. So Horizon Brave says, Fraser Kane, have you seen the buying cost for Starlink? It's insanely expensive. I don't see how the price is providing it to everyone. It's still restrictive in price. So I think it's important when you look at something like Starlink. Yeah, the buy-in price for Starlink is like $500 for the receiver, and then you pay something like $75 a month. But you've got to compare that to existing satellite internet, which is roughly the same and terrible, or trying to run a wired internet out to somewhere in the middle of nowhere. You're looking at tens of thousands of dollars, millions of dollars. Once you set up one Starlink receiver, say at the library in your city, in your little town, then you've now got high-speed Wi-Fi that anybody can come and use. So don't look at it like an individual replacing their existing Wi-Fi internet connection with Starlink. It's literally providing internet for the first time in places that there's no other solution. My parents, I've mentioned this before, my parents live on this small island off the coast of Canada. The best they can do is about, I think, 1 megabit up and down. Going there, trying to use their internet is torture. But there is a city hall, so there's a fire hall where I think they can set up a higher speed internet connection and then radiate internet out from there. So it's more about not having to have that last mile to be able to connect this stuff. And so I think you're going to see there's some great stories about people setting up Starlink in reservations in the United States that nobody wants to give them internet. And suddenly, here you go. You've got internet. Setting up internet for people who are fighting a forest fire. It's not like each person needs their own Starlink. You just need one that then everybody can access. And that's the part that we haven't figured out. And of course, we're going to see prices come down fast as there's more competition and the technology gets accelerated and so on. And for most people, it's not for them. It's not, if you live in a city, if you have kind of mediocre internet from whatever awful cable provider you have, it's not for you. It's the person who has no other option. Like literally, would you like internet? That's a shame because you don't get any. Those are the people this is for. Teox Trader asks, how can the Methuselah star be older than the universe? It can't. So there is a star that if you estimate based on the chemicals that are in it, it appears to be a little older than the universe. So either the universe the measurement age of the universe is wrong, or the measurement age of the star is wrong. You have to have a universe first before you can have a star. So one of those numbers is wrong. And it's just a matter of figuring out which one it is. I'm going to guess it's the star because the measurements of the age of the universe are really good, while understanding the chemical processes that are going on in stars and using that as a way to figure out exactly how old they are, it has gigantic error bars. So I'm sure over time, astronomers will narrow down the age of the star until, it fits within the universe. It's very old, though. All right. Joe33, if we have the Oort cloud, wouldn't other star systems have something similar? If so, why haven't we directly observed one to prove the hypothesis? We can't observe our own Oort cloud, and we're inside of it. So how can we find a Oort cloud around another star system? Now, astronomers have detected cometary rings in other star systems. In some cases, actually, there was news that just came out today. Astronomers have detected the carbon monoxide that is coming from the comets in an asteroid belt that are getting worn away by a new star. So the star has just started to really blast out radiation, and it's clearing out all the volatiles from its asteroid belt. And so you're seeing sort of dissipating comets being blasted away, which must have been a phase that happened here in the solar system a long time ago. And there have been other examples where it looks like you can detect comets smashing into each other in other star systems. But the Oort cloud is a much larger, like the cometary belts that we have here. We have the Kuiper belt, and trans-Neptunian objects and things like that. And they're only out around, say, the orbit of Pluto and a little beyond. But the Oort cloud can extend for a light year away from the sun. It's halfway to Proxima Centauri. You could still theoretically find Oort cloud objects. And so you wouldn't just see them with a telescope. You would need to see them interacting, causing some kind of light that would make them visible, or detect their interactions through gravity. It's only when they get really close to the star. So just imagine what it would take to detect a comet in an Oort cloud in another star system. You would need to be able to have a telescope that was powerful enough to detect a comet that was in another star system that was on an orbit that where it got brightened up as it was getting close to the star. And then you would be able to watch it for a bunch of nights, and then you would be able to calculate the trajectory of the comet to confirm that that other star system has an Oort cloud as well. So yeah, it would be incredible to do that. So we just don't have that capability yet. So stay tuned. Gaurav Sharma asks, if Andromeda doesn't have a supermassive black hole in its center, what are the stars revolving around? So Andromeda does have a supermassive black hole at the heart of it. In fact, while the supermassive black hole at the heart of the Milky Way is 4.1 million times the mass of the sun, the one at the heart of Andromeda is 100 million times the mass of the sun. So it's 25 times more massive than the black hole that is at the heart of the Milky Way. But I'm sure the one you were thinking of is the one that's in M33, which is the Triangulum galaxy. And that is the other big galaxy that's part of the local group that in the far future is going to merge with Andromeda and the Milky Way. Like the three big galaxies in our area, right? Milky Way, Andromeda, and M33, and Triangulum. And it appears that Triangulum doesn't have a supermassive black hole at its heart. And so at some point in the ancient past, it absorbed a galaxy and the supermassive black holes collided. And in certain situations, they can actually bounce and one can be ejected. And so it's possible that Triangulum's supermassive black hole was just ejected out of the galaxy. And now it's just freely floating through the universe. But your question is really like, how can that work if it doesn't have a black hole? Well, the black hole is not the anchor of a galaxy. When you take all of the mass of the Milky Way and then you take the mass of the supermassive black hole, it accounts for a fraction of the mass, like 0.1. I think we talked about this a couple of weeks ago or months ago, that it's like 0.1% of the mass of the Milky Way. The anchor of the galaxy of the Milky Way is not the black hole. It's just like another thing. It's a heavy object that's sunk to the middle of the Milky Way and it's just hanging out there. And if we had the black hole or didn't have the black hole, it would be exactly the same. What really is the anchor of the Milky Way is the gigantic dark matter halo that surrounds the entire Milky Way. That is, what we see as the stars is this, is this tiny little spiral that's embedded in this gigantic halo of invisible dark matter that's providing 85% of the mass of the Milky Way. And that's what's turning, and the Milky Way is embedded inside of that. So that black hole is nothing. Zach Perry, has the Event Horizon team made any progress on imaging the corona of Sagittarius A, or is there just too much stuff in the way for it ever to be possible? We don't know what's going on with the attempt to image the black hole at the heart of the Milky Way. So remember that first image of a black hole that we saw? That was the one from M87, which was like 100 million light years away. We still don't have the image of the black hole. Like they captured an image of M87 and they captured an image of the black hole, SagA, and we don't have that one yet. And when M87 came out, I'm like, where's SagA star? And from what I can tell, and this is sort of the journalisming that I did, I believe that's a technical term, was that the environment around SagA, because it's smaller and closer, is a lot more dynamic and a lot more difficult and computationally intense to try to render down into useful data. And so they did M87 as like the test to make sure that they're doing, because the features on M87, it's so big, it's moving so slowly that they unfold over the course of weeks, while at SagA star, at the heart of the Milky Way, it's turning around and they're unfolding over the timescales of hours. And so it's just a much more complicated challenge. But it may very well be that we see future versions of the Event Horizon Telescope capturing images of other supermassive black holes before they finally get around to releasing the one from SagA. So stay tuned. All right. Raphael Dominichini. If an object the size of the Earth fell into the sun, what would happen? What impact on Earth? Nothing. It would cause a flare on the surface of the sun briefly, and then it would be gone. And the sun would be glad to consume a little more mass. It's hard to really wrap your head around how much of the solar system is the sun. It's 99% of the mass of the solar system, and the rest is Jupiter and Saturn. Earth is nothing. There are dozens, hundreds, thousands of times the mass of the Earth of like rocky material inside the sun. The sun could eat Earths all day long and it would have no impact whatsoever on the sun. Like maybe we would see a brief smear and then it would be gone. Like remember when Jupiter gobbled up comet Shoemaker-Levy 9 and we saw these bruises on the surface of Jupiter for a little while and then it was gone. So no, the Earth would cause no impact whatsoever on the sun. Mark Starkiller. Have you played the Elite Dangerous video game? It has 400 billion solar systems in a one-to-one map of the Milky Way. If you did, would you agree with me that aliens will never visit us? The argument that I always make is that Oumuamua and now Comet Borisov have visited us. So in like 2 years, we've detected 2 rocks that have visited us. And so if a rock can visit us, if a rock can make the journey, then why can't aliens, like smart rocks, as opposed to just rocks? So even though space is huge, time is on your side. You should be able to make that journey. But remember, like if you're saying that if aliens will never visit us, then that means we'll never visit anyone else, ever. That you can't have it both ways. Like either we can go to other star systems at some point in the far, far future, or we can't. And I like to think that we can. And so that's why I think that no one has visited us is because they don't exist, not because they can't. But that's my opinion. Dennis Tyrant, how can Andromeda have a more massive central black hole than Milky Way despite Milky Way being more massive than the Andromeda galaxy? It's not. Andromeda is the vastly more massive galaxy than the Milky Way. So, no, Andromeda is a bigger galaxy than the Milky Way. By like a lot. I forget the exact number. In fact, the numbers are getting closer. Like I think in the past we used to think it was like 1 trillion stars in Andromeda to 100 to 400 billion stars in the Milky Way. So now I think the ratios are getting a little closer to each other, but still like it's a factor of 5 times more than the Milky Way. So it's far more massive. Apologies. Chimpy726 asks, any up-and-coming propulsion systems that have piqued your interest? The one, I think I've mentioned this on a couple of shows, the one that I'm most excited about, and this is going to seem really weird, is I'm really excited about an air-breathing ion engine. This is a piece of research that's coming out of the European Space Agency, and they're working on building ion engines that can bring in parts of the Earth's atmosphere and then eject them again using solar panels, using electricity as a form of acceleration. And so you no longer need a propulsion, like you don't need to carry propellant on your spacecraft. You're getting your electricity from the sun and you're kicking you're just grabbing pieces of the atmosphere and then you're accelerating them again. And of course, this only works when you're in a very low altitude, but it would be really interesting to see how low we could fly a spacecraft and still have it be able to operate and still maintain its altitude, all the while that it is not using any propellant. Like, could we have a satellite that operates at 150 kilometers as opposed to 500 kilometers? That would be really interesting. The closer you get to the surface of the Earth, there's actually a ton of benefit. You get much better photographs. So if you're doing like land monitoring and weather and things like that, better communications. It's a lot safer in terms of space junk because your satellite just will re-enter the Earth's atmosphere the second your ion engine cuts out. So actually, that's the propulsion system that I'm most excited about, is air-breathing ion engines here in the atmosphere of the Earth. So I'm probably going to try and bring on a specialist to talk about that. Hal McKinney asks, is the sun net gaining or losing mass year over year? It's losing mass. So the sun is giving off both, it's turning hydrogen into helium at its core, and so it's blasting out light and photons. They start out as gamma radiation, and they make their way and they become visible light when they get to the surface. So that's a loss of mass. And then it's also losing mass through just the solar wind, which is leaving. But it's not a lot. And I forget the exact amount. I think I looked this up at one point. It's losing like the mass of the Earth every 100 million years or something like that. So it's not a lot of mass. Trey Harmon. Just curious, do you have any idea why so many comets have been discovered this year? New telescopes, initiatives, techniques, or just because it's 2020? Yeah, it has been a good year for comets. I mean, we had pretty much the first visible comet that, you could see with the unaided eye in decades in the northern hemisphere. And it was not great, but at least you could see it. Like, we went out onto the back deck and we had a perfect view towards the comet, and you could like squint your eyes, look over the side, and you're like, there it is. And then in binoculars, you could definitely see it. And we got a chance to take some pictures. There's a lot of really great automated sky surveys that are going on now. There's Pan-STARRS. A lot of these are searching for asteroids, potentially dangerous near-Earth objects, but they're also turning up a lot of these comets. That's why they all have very similar names: Neowise, Pan-STARRS. It's not like we keep seeing the comet Pan-STARRS. It's that you're getting a ton of comets named after the Pan-STARRS robotic observatory. And so chances are it's all going to be Vera Rubin. Comets, asteroids, they'll all be named after the Vera Rubin observatory. They're going to come up with some special naming technique, because it's going to be finding so many comets first before anybody else in the southern hemisphere anyway. All right. Amo asks, do you think that fusion can make a difference and help propulsion in the near future? Fusion, nuclear fusion, of course, this is what the sun is doing. We have, there have been attempts to create fusion, controlled fusion here on Earth. Of course, a hydrogen bomb is fusion. The most powerful bombs ever built are fusion bombs, but you can't really control them that well. So the holy grail has always been, can you make a controlled fusion reaction that will produce more power into it than you produce out of it, and not detonate your fusion plant like a bomb? And the sort of, people have been chasing after this goal, and the joke is always that fusion is 30 years away. 30 years ago, fusion was 30 years away, and it's 30 years away today. But there's the ITER project in Europe, which is sort of like the first big scale fusion project that's going to try to actually create net positive energy with fusion. It should come online in the next 5 years or so. They're going to do their first experiments, but it'll be still decades before you've actually got fusion plants that are providing energy to the grid. So you've got to go through that whole process of like making fusion work, like just making it work at all. And then you've got to be able to make fusion work in the complexities of space, in when you're dealing with, you know, the harsh environment, the radiation, the lightweight materials that you have to use. So I would say we are 50 years away from a fusion engine, 100 years away. It's going to be a long time. And I know The Expanse has told you that we should have it soon. We're a long way away from that. Now, there are some ideas that are kind of like fusion that have been proposed. We've done a couple of, we've talked about them a few times in video, and some of them have been like, there's one that got awarded a NIAC prize, you know, NASA's Advanced Innovative Concepts Award. And I don't remember exactly how it works, but not exactly fusion. And there are some other interesting fusion experiments. I think Lockheed Martin is working on one, and there's some others. So who knows? Somebody may be able to come up with an idea that is suddenly, boom, fusion. It's compact, you know, Mr. Fusion. You just throw some garbage in it and boom, you got a fusion reactor. But at the path that's going on right now, we're looking at decades and decades, if not a century, before the power of fusion is harnessed. Which I know you want it tomorrow, you want it now, but it's going to be chemical rockets, ion engines for a long, long time. Right. Raphael Dominichini asks, how can we destroy Saturn's rings? Nuclear weapons, shooting asteroids towards the rings, lasers? It's a good question. I think what you probably want, if you want to destroy Saturn's rings, you probably want to like spiral a moon into Saturn. So you want to like take one of its moons, set up some kind of like gigantic mass driver on the moon, like maybe take, I don't know, Rhea or something like that, which is pretty close in. It's already interacting a bit with the rings. Put a mass driver on it or some kind of fusion engine. Slowly, slow down the orbit of the moon so that it spirals into Saturn, and then the rings will impact it, and then it'll finally crash into Saturn and be destroyed. And then Saturn will have no rings. Why would you want to do that? You're a monster. But if you did want to do it, that's how you do it, I think. So Evan Moyle asked a super chat question. Has there been any feedback from other astronomers on David Kipping's Terrascope idea? I'm sorry, I don't know. You should ask David. I should ask David. I'll get David to come back. We'll chat. We'll do another interview with David, and we'll ask him what's happening with the Terrascope. It's such a great idea. But there's a lot of these kinds of projects that are out there that's like a really clever idea, but it would require a lot of infrastructure for us to be able to actually use. And it's tough. That idea of setting up a telescope out 1,000 astronomical units from the sun, using the gravity of the sun as a lens that would allow you to see aliens reading newspapers dozens of light years away. But you need to be able to deploy a telescope out to 1,000 astronomical units is tough. So it's hard. It's hard. Like I feel like my job, unfortunately, I don't know how I got this job, but my job is to just tell you what's coming up next, not what could happen in 100 years. So beyond about 10 years from now, everything just looks really hazy to me. Isaac Grimes, I just got my wisdom teeth taken out. The anesthesia I was administered made time go by wicked fast. Could we maybe use that to help astronauts deal with long travels? It's an interesting idea. Anesthetize, essentially put a bunch of astronauts under so they don't have to deal with the time of spaceflight. The idea that has been suggested, in fact, NASA has been studying this, is this idea of hibernation, that you, hey, Torin Atkinson, hey, Torin, have I ever worn a spacesuit? No. You should talk to Everyday Astronaut and Scott Manley. They've got spacesuits. I'd love to wear a spacesuit. I've worn a spacesuit glove one time. So I got a chance to actually try on one of the spacesuit gloves, and they're really hard to use, but I've never actually worn any other part of a spacesuit. Sorry. All right, back to the question. Sorry, Torn is a friend from Vancouver. Okay, anyway, yeah. Hibernation. So you can, so doctors have been able to put people into a state of suspended, into a state of hibernation. They essentially cool your body down and put you to sleep. And they do that so that they can sort of respond to various medical situations. But it's thought, wow, the body slows down, their temperature cools down, they require less resources. Maybe you can keep a human body, keep an astronaut alive for a long space flight in this sort of state of kind of like hypothermia. And so there's been some proposals with NASA to actually do this. And so the benefits would be that you would require way less resources. You would essentially put all of your astronauts to sleep except for one at a time who would remain awake, taking care of the rest of the astronauts. Now, they wouldn't actually be like frozen or like an alien, like in a state of suspended animation, but they would have a very low heart rate using very low amounts of oxygen, require very little nutrients in their body, and then they would wake them up on a regular basis, and they would sort of work out the kinks and make sure there's no long-term effect, and then go back to sleep. So that's been proposed, and in fact, you could have a spacecraft go to Mars or even farther out into the solar system for a fraction of the resources that you would require just having everybody awake and floating around inside the spaceship. But I wonder if people would be willing to do that. I don't know if I would. To essentially be almost killed. Just almost brought to death in order to make a trip to Mars. It'd be kind of scary. So I don't know. Tom Garcia says, but cold fusion is just 5 years away, right? Don't count out cold fusion. Someone will figure that out. I don't know if anyone's ever going to figure that out. Cold fusion, I was a kid when cold fusion was first announced, and it was sort of, they made a horrible mistake in the way that they communicated the information and the science that they had done. But I know people have been trying to figure out if there's any there, and I'm not sure what the current state of cold fusion is. I'm assuming it's gone nowhere, but every now and then I read an article on Wired or Ars Technica or something like that where someone says, cold fusion, ha ha ha, but actually there might be something there. People are still looking into it. There's something going on, but we don't know what it is. Don't expect anything amazing, but maybe there's some new science to be discovered. So see what happens. Let's see. Apologies. I'm just going to go back a little bit, get some more questions. Mark Starkiller says, I know the hot Big Bang was proved and it took a long time to get to this, but isn't it easier if our universe did start in a hot Big Bang? Please share your thoughts about this. I don't know what you mean by easier. Like, are you saying that the math is easier if the universe didn't start with a hot Big Bang? Or it's just like, what does that mean by easier? Like, quantum mechanics is not easy, and yet it's clearly you can use the mathematics of quantum mechanics to predict reality in a very very careful, very accurate way, and yet the kinds of weirdness that happens with quantum mechanics is not easy. So I don't really understand the question exactly. the universe just appears to be the way it is, and that we know that as you look at the universe today, everything is moving away from everything else. And so that tells you that in the past everything was closer together. And if you keep putting things closer and closer together, you get to this time when the universe was so close together that essentially the entire universe was like a star. And if you did that, then you would see this glow in all directions. And what do you know? You see this glow in all directions. So it's like there's evidence that the universe was hot in the beginning, and then it has cooled down over time. So it's just like the evidence seems to say that that's what the universe used to be. I don't know what you mean by easier. It just is. Sometimes, like, you follow nature just wherever nature tells you to go. Nature just reveals its secrets one at a time, and some of them are really easy and satisfying, and others are uncomfortable and unsatisfying, and it doesn't matter because that's just nature. Dennis Tyrant, do you think that there could be planets in the globular clusters? Globular clusters, yeah, globular clusters are, of course, these incredible ancient relics that are thought to be extracted from other galaxy collisions, and they can contain hundreds of thousands, even millions of stars. They're like buzzing around in this really tightly packed ball. And astronomers use them for all kinds of really cool things. They use them to calculate overall stellar populations, to sort of run various experiments, observational experiments about how stars change time, their compositions, and they've even been able to detect what looks like stars that have been colliding with each other inside these globular clusters. But the question is, could you have planets in them? And I think the jury is still out on whether or not you could have planets on them. It would be incredible to be on one of these, because you would see, like, on average, stars are about 5 light years apart in the Milky Way. But in a globular cluster, stars are about a light year apart. And so the entire night sky would be filled with stars that are as bright as the brightest stars that we see in the sky, and brighter. There would be, when you think about stars like, say, Rigel or Betelgeuse, right? You would see stars that are brighter than that. It would be like a constant glow at all times. But the thinking is that the gravitational interactions of all of these stars zipping past each other is going to disrupt the planetary systems. There's actually some research that came out earlier this week talking about how in the far, far future, like the vast future, trillions of years from now, the gravity of the Milky Way is going to dismantle the Milky Way. Sorry, it's going to dismantle the solar system. It's going to one by one take away all of the planets. It's going to just move them away from the solar system. Obviously, the sun will have bloated out like a red giant, collapsed down into a white dwarf, probably ate Mercury, Venus, maybe even the Earth. But then the gravitational interactions from all these stars, one by one, will just kick Uranus, kick Neptune, kick Jupiter, Mars out of orbit from the solar system, until all that's left is just the white dwarf that was once the sun, which would suck. John Suffield, oh, you want to know about the Great Attractor? Every week, watching you. All right, you're going to have to go back a couple of weeks to get that joke. All right. Wait, when? Trillions of years from now. We got like 2 minutes. Let me see if I can find one more. Hal McKinney asks, where do all the gazillions of solar neutrinos go? How do we know that neutrinos aren't the dark matter? That's a great question. And so neutrinos, of course, are these particles that are produced in reactions in the sun. They're passing through your body right now. There are millions of neutrinos in your body. You don't feel them because they don't interact with anything. And for the longest time, astronomers thought that maybe neutrinos would explain dark matter. But the problem is that, and I don't have time to kind of go into all the nuances of it, but essentially the behavior of dark matter matches a particle that has to be slow moving and not fast moving. Neutrinos are moving really close to the speed of light. and so they're considered hot. And so when you hear this terminology that astronomers are looking for cold dark matter, what that means is they're looking for a particle that is moving slowly, as opposed to neutrinos, which are moving very quickly. Because essentially, if you take the behavior of neutrinos, they don't match up with the observations that have been made for dark matter. And so, unfortunately, neutrinos have been ruled out as an explanation for dark matter. Although neutrinos definitely account for some of the mass of the universe, for sure. All right, we've reached the end of the episode, and those were all the questions. So thank you, everybody, for joining me this week. I really enjoy this. It's a lot of fun. I hope you guys enjoy it as much as I do. Like I said, some cool interviews coming up this week. We've got the weekly Space Hangout, another episode of Astronomy Cast coming up. I hope another great virtual star party coming up on Saturday, assuming the weather and the technology holds. More interviews coming up. And of course, we've been absolutely crushing it on Universe Today. I hope you've been enjoying the coverage on Universe Today. I feel like we've been doubling the amount of content on the site. Great stories, a lot of really great writers, and I couldn't be prouder of what everybody is working on Universe Today. That's the thing that we have been putting the most emphasis on. So I hope if you're not reading Universe Today, you should. And of course, you should be signed up to my weekly email newsletter, which encapsulates all of that into one document that goes out once a week. You can get that from universetoday.com/newsletter. All right. Thank you, everybody. Thank you to the mods. Thanks to Nancy for copy pasting all the questions so that I can read them more easily. Couldn't do this without you, Nancy. All right. We'll see all of you next week. Thanks, everyone.